Hi everyone, this is the second example from chapter 9. It is question 198. Let's read the question. Question 198. What is the magnetic field at P due to the current I shown in the wire above? So what we are shown on the diagram is we have a point P here where we want to calculate the magnetic field, and there's a weird current carrying wire around it. So this current carrying wire has four sections. There's two sections that are strictly aligned with the point P. So this first section and this one, and then there's two semicircle with different radius. Okay, so basically we need to consider the magnetic field caused by each of these four current carrying section. All right, so I'm gonna split them. I call this one over here B1, the bigger half circle B2, this section B3, and the smaller half circle B4. Now we will use the formula in the right hand rule to determine the magnitude of the magnetic field and the direction of the magnetic field. So for the formula, using the Biot-Savart law, we concluded that for a partial circle, we could find the magnetic field at a point in the center using that formula over here. All right. We also concluded that at the tip of a current carrying wire, there was no magnetic field. Well, if we look at B1 and B3, that's exactly the situation we are in. The point P is at the tip of B1 and B3. In other words, B1 is equal to B3 is equal to 0. There's no magnetic field due to B1 and B3 at point P. All right? So that means there's two sections that will create a magnetic field. There's section B4 and there's section B2. Now let's talk in terms of B4 at the beginning. We want to find the direction of the magnetic field. What we do is we point the current with our thumb and the finger are pointing toward the magnetic field. Now note what happened here is we have a loop, it goes into the board and then come out of the board. Because of the way it is, above the wire, the current is coming into the board and then it's coming out. So from the point of view of B4, from the point of view of P, B4 is creating a magnetic field pointing outside the board. Now, an important point we need to mention here. If I were to draw a force diagram or a vector diagram, we will have the positive X pointing to the right, the positive Y pointing up. In the case of the Z-axis, the third axis, it is positive when it's pointing out of the board, and it is negative when it's pointing into the board. What that means is B4 will create a positive magnetic field here because its magnetic field is pointing out of the board. That's important, okay? And that's by convention. Basically, the Z-axis could be determined by the right-hand rule itself. We point toward the X, curl a finger toward the Y-axis, and the thumb is pointing the positive Z-axis. All right? Now, let's have a look at B2 in this case. We follow with our thumb the current. And in this case, we can see that the finger will be pointing inward. So we have the magnetic field coming out of the board and then coming into the board. From the point of view of B2 at point P, the magnetic field is negative. So B4 is positive, B2 is negative. Both of them are pointing in the Z direction, okay, in the Z direction, sorry. All right, so now we simply need to combine both of these. We have the net vector is equal to B4 plus B2. And note, I'm gonna add something here. All of this is happening strictly in the Z-axis, so let's add the unit vector Z over here. So we replace B4 by this formula over here. So we got permeability of free space multiplied by the current. We don't know these values yet, by the way. We are just looking for general formula in this case. Multiplied by the angle divided by 4 pi r. Okay, so there's two variables here that we can set. We got the angle and the radius. So the angle, it's the angle of the partial circle. Well, it is a partial circle. In this case, it is a half circle. If it were a complete circle, the angle will be 2 pi radian. This is half a circle. The angle is therefore pi. So we got the angle pi over here. The radius from the point of view of B4 is simply the distance between the half circle and the center of curvature. It is the radius A in this case. So we got A. Following the same logic for the bigger half circle, this one, again, the angle is pi. The radius is different though, it's B. So I'll replace the B over here. Then I isolate the value and we get this formula, which is the permeability of free space, multiply by the current, divided by 4, multiply, we open the parenthesis, 1 divided by A minus 1 divided by B in the Z direction. Okay, so that's important. Yeah, so that's it with this question. The question 195 and this question really combine every concept to determine the force from a current carrying wire and its direction, okay? Make sure you practice these. I can guarantee you that there's a question on the test that will be similar and that will use these concepts, okay? There's no avoiding it. Now, we will be solving some more problem between two current carrying wires, or two parallel current carrying wire in the next video, all right? So see you in the next video.